Friends, students, dear chemistry Padawans, it is time for another video, and we are going to be talking now about electron configuration in our third unit. So we talked about measurement and uncertainty, and then we talked about the particulate nature of matter, and now we are moving on to electron configuration. So again, most of this should be reviewed, just going a little bit more in depth compared to last year. Okay, so I've already showed you this slide before, but to remind you guys, the electromagnetic spectrum is a continuation of different energies that is represented by a range of wavelengths and frequencies, with energy on the higher end of the spectrum be associated with higher frequency and lower wavelength, whereas energy on the lower end of the spectrum is associated with low frequencies and long wavelengths. And that is related by the equation, the speed of light equals wavelength times frequency. Now it is denoted as F in your data booklet rather than the V, just letting you guys know. And then the visible spectrum is only a small portion of the electromagnetic spectrum, ranging from about 400 to 700 nanometers in length. So we talked about the hydrogen emission spectrum before. This is a slide you've already seen. Just to recap, when the electron in hydrogen gains energy, the electron moves up to different energy levels, and then when it falls back down, it releases photons of light of specific wavelengths. So we see specific colors. So specifically, transitions from the 6th energy level down to the 2nd one would produce this violet light. From the 5th to the 2nd produces this blue. The 4th to the 2nd produces this green, and the 3rd to the 2nd produces the red. And the reason that the red color is seen for the smallest energy transition is because it takes the least amount of energy to move from the 2nd to the 3rd energy level. So we're going to see the longest wavelength of light, which is red, of visible light.
Hey, apologies guys. I know I look different now, but it cut off recording when I was trying to do this last time, and now I think I have the plague or something, so I am very sick, but I'm going to get through this video for you guys. Okay, so we're going to talk about how to actually calculate the energy during an electron transition using the following equations. Energy equals Planck's constant times frequency, and the speed of light equals wavelength times frequency. Then if you combine them together, you get energy equals Planck's constant times speed of light over wavelength. Please note that the wavelength has to be in meters because the speed of light is listed in meters per second. So if you look at this diagram over here, you can see an example of different energy transition series, and this first ring here represents the first energy level, n equals 1, and then 2, 3, 4, 5, and 6. So the visible spectrum, the Balmer series, you can see that you can only see transitions between energy level 2 and 6, 2 and 5, 2 and 4, and 2 and 3. And this is the absorption series because it's showing that the energy is being absorbed from a lower to a higher wavelength. But you also can have emission spectra. So they're the exact same energy, just moving in the opposite direction. So just know if the arrow is going up, the energy is being absorbed, and if the arrow is going down, the energy is being released. So this the Lyman series here is ultraviolet because there's a bigger energy gap between 2 and 1, and so that's actually too much energy to be visible. So between 1 and 2, 1 and 3, 1 and 4, 1 and 5, 1 and 6, that's the Lyman series. And then the Paschen series is the infrared series, so it's a little bit shorter, or wavelength, not shorter wavelength, I'm sorry, shorter energy and longer wavelength, so we can't see this because the energy is too low. So here's an example. I have calculated the convergence limit for hydrogen atom has a wavelength of 91.16 nanometers. And the convergence limit is just talking about the ionization energy, because we know that as energy levels get farther and farther from the nucleus, they get closer and closer together, or they start to converge. So the convergence limit is the same as the ionization energy. So it tells you that that wavelength is 91.16 nanometers. So what I can do is plug that wavelength into this combined equation here, but turn that nanometers into meters by multiplying by 10 to the negative 9th. Then I would get my answer in joules per atom because the Planck's constant is in joules. So your answer will be in joules. But it is for 1 atom or for one photon. In this case, I was talking about for the hydrogen atom. So I just can multiply it by 6.02 times 10 to the 23rd because that is how many atoms are in a mole. And in that case, I would translate my ionization energy from joules per atom to joules per mole. And then normally these ionization energies are reported in kilojoules per mole, or energies in general are in kilojoules per mole. So to convert from joules to kilojoules, just divide by 1,000 and we get 1313 kilojoules per mole, which is how much energy it would take to remove an electron completely from a mole of atoms. Okay, so moving on, now we're going to talk about how these orbitals are organized in atoms. So we've already talked about the main energy levels. Those are also called energy shells. They are indicated by the quantum number n. So n is just a representation of that entire energy level. And there are different quantum numbers that represent different characteristics of orbitals, but we're not required to know those for IB, but I just wanted to let you know that they do exist. So only a fixed number of electrons can exist in a main energy level, and that is represented by 2 times the energy level, or the principal quantum number squared. So for instance, in the first energy level, that would be n equals 1. 1 squared is 1, times 2 is 2. So 2 electrons can exist in that first energy level. And then using that same formula, you can see that there can be 8 electrons in the second energy level, 18 in the third, and 32 in the fourth. However, those main energy levels are split into sublevels, which represent different shapes. There's S, P, D, and F. So S sublevels, those consist of orbitals that are spherical in nature. P sublevels have orbitals that are in a dumbbell shape. D orbitals are like a flower shape, and I'll go over this later. In F orbitals, what they look like. So each sublevel can only contain a fixed number of electrons depending on how many orbitals it has. So an S orbital that only contains 2 electrons, there's only one S orbital. There can be 3 orbitals in a P sublevel, so it can contain 6 electrons. There can be 5 orbitals in a D sublevel, so it can contain 10 electrons, and there can be 7 orbitals in an F sublevel, which can contain 14 electrons, because remember, 2 electrons per orbital. So looking at different energy levels, you can see in the first energy level only has one S sublevel with 2 electrons. The second energy level has an S and a P sublevel, which makes sense because it can contain 8 electrons. The third energy level can contain SP and D sublevels, and then the fourth SP, D, and F. And any energy level after that would also contain SP, D, and F sublevels. So remember that these orbitals are in discrete energy levels. Each orbital can hold a maximum of 2 electrons, and they are spinning in opposite directions. So one of the quantum numbers actually represents the spin state of that electron. So if you look here, this is an orbital diagram showing like visually the difference in energy levels between the sublevels. And you can see that there's a big jump in energy between 1s and 2s, but then as we get farther and farther up in the number of energy levels, the energies get closer and closer together, and you can see that the difference between S and P, 2S and 2P are very small, and even smaller between S and D. So you can actually see that this 3D sublevel is actually higher in energy than the 4S sublevel. And you can also, because of this, determine that electrons will fill the 4S sublevel before the 3D, because electrons always try to fill energy levels that are lower in energy before moving to higher energy levels. So even though this 3D sublevel is in the third energy level, the electrons will actually go into the 4S sublevel in the fourth energy level before filling those 3D sublevels. So if you look at the periodic table, it has an organization that splits into S, P, D, or F sublevels, and it actually is arranged in such a way that you can know the order that these sublevels are filled. So if you move left to right, top to bottom, you can see that the 1s is filled first. This represents hydrogen and helium. So for this hydrogen atom, for example, there'd be 1 electron in the 1s orbital, and helium would have 2 electrons in the 1s orbital. Then moving down, this is the 2s sublevel. So if you have electrons for elements like here, I know lithium is right here, so it would have electrons in the 1s sublevel and then one electron in the 2s sublevel. And then you just keep filling them left to right, top to bottom. And then you can see when you get to this fourth energy level here, the 4s is filled before the 3d. And again, that's because the 3d is higher in energy. And this is where we start getting into the transition metals. So D and F sublevels are represented by these transition elements here. And also this lanthanide series here is the 4f sublevel. So the order of filling can get kind of complicated when you get down here. And that's because these energy levels are so close together. And so certain combinations will be more stable than others. So there's no hard and fast like rule when it gets down here to these F sublevels. There's lots of there's a rule, but there's a way too many exceptions to that. And so I'm going to be talking about that in a minute. But when you get to the 6s sublevel here, this is where the lanthanides are right in here. So after 6s is actually going to be 4f and then 5d and then 6p. So again, remember right here is where the lanthanides and actinides are in the periodic table. So the definition of an atomic orbital is it is a description of the volume in space where there is a high probability that an electron is located. Because remember, the quantum mechanical model denotes that electrons are only in probability regions. So that is what the definition of an orbital is. And according to Heisenberg's uncertainty principle, you can't state the exact position of an electron at a precise moment in time. And that is because you can know where it is or how fast it is, but not both, because if you try to measure where it is, you affect how fast it's moving. And here is the shapes of what these orbitals look like. As I told you, it's spherical in nature. The p orbitals are dumbbell shaped, and notice there are 3 different p orbitals, and that's because, remember, the p sublevel has 3 p orbitals, so we have px, py, or pz, and that's just describing its orientation along the xyz plane. And then you can see d sublevels look more like a flower shape, and except the 5th d orbital, which is this weird looking, I call it like a pacifier looking thing, like I don't know, it reminds me of like a pacifier, like at the donut around it or something, I don't know, but it's a very weird shape. But again, these just depend on the orientation of these orbitals in space. And then I call F orbitals a little too much because, like, seriously, look at these things. These are crazy trying to draw these. So these are the 7 different F orbitals you can have. And again, that 7th one looks more like a double pacifier or something like that. But yeah, here's what they look like. So how do electrons fill these energy levels? Well, we said that they like to fill orbitals that are lower in energy before moving to orbitals higher in energy. So this is called electron configuration. And you can deduce the electron configuration by following these 3 rules. The first is the Aufbau principle, which again is electrons fill lowest energy levels before higher ones. And if you look here, if you look at these arrows, it tells you the order in which orbitals are filled. So 1s, 2s, 2p, 3s, 3p, 3s. 4s, 3d, 4p, 5s, 4d, 5p, 6s, 4f, 5d, 6p, 5f, and 6d, and then so on. Hund's rule states that if 2 or more orbitals of equal energy are available, so example, you have 3 p orbitals in the p sublevel, they're all of equal energy, the electrons will occupy them singly before pairing up. So if an element has electrons in the p orbitals, they're not going to join the same orbital if they can help it, because those electrons are actually going to, sort of repel each other if they're in the same orbital, because they're both negatively charged, and so they would rather be alone before being paired up. So that's Hund's rule. And then the Pauli exclusion principle says no 2 electrons can have the same 4 quantum numbers. And remember, I told you quantum numbers are just descriptions of these electrons in space. So no 2 electrons can occupy the same space is basically what this is saying. And each orbital can contain a maximum of 2 electrons only, but again, they can't be the same type of electron. One has to have the opposite spin as the other. So this is an orbital diagram as I've shown you before, but it's useful for showing Hund's rule because it can show you that electrons would rather occupy single p orbitals here, or any orbital for that matter of the same energy, before they pair up. So this, for example, is an element with 1, 2, 3, 4, 5, 6, 7. So this is nitrogen. Nitrogen will have 3 electrons each in a p orbital, and then when you get to the next element, which is oxygen, the next electron will then pair up with this one in the 2p orbital. So the electron configuration is showing the number of electrons in the main energy level and in the type of sublevel in which they exist. So the 1 denotes the energy level, and the letter represents the sublevel, S, P, D, or F, and then this superscript represents the number of electrons in that energy level. So for nitrogen, it would be 1s2, 2s2, 2p3. And I listed elements, electron configurations for the first 3 energy levels here. There are some elements that don't follow these rules, and we'll get into those exceptions in a minute. I also did want to point out that sometimes in IB they don't do this in a very consistent manner. I told you that 4s fills up before 3d, which is absolutely true. So if you wanted to write, for example, scandium as 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d1, that is perfectly acceptable because you're just moving from left to right, top to bottom on the periodic table. But sometimes they list that 4s after the 3D because they just want to go like 1, 2, 3, 4. So if you see it that way, it does not mean that this D sublevel fills up before the S. They're just writing it to be, I don't know, confusing. But I just wanted to point that out. Sometimes you'll see it written like this. Okay. And then there are noble gas configurations, which build upon the electron configuration of the last noble gas. So it's basically a shortcut method. If you have any element that comes after a noble gas, which, you know, unless you're hydrogen, there is a noble gas configuration for that element, you can put the noble gas before it and then just start your electron configuration from the next element. So you can say phosphorus contains the same electron configuration as neon plus 3s2, 3p3. It's just a shortcut, easy way of not having to write 1s2, 2s2, 2p6, 3s2, 3p6 for like, especially if you have an element that's, you know, farther down in the periodic table. No one wants to write all that. So I wrote some elements here for standard D block configurations. You can see we already talked about scandium and titanium, vanadium, manganese. I have iron and zinc here, but whenever you try to write electron configurations for ions, the electrons are going to be lost from the S sublevel before the D. So for example, iron's configuration is 4s2 3d6 normally, but if you have an iron 2 plus ion, those electrons are going to be lost from this 4s. So instead, it would just be argon and then 3d6. You don't have to write 4s0, you can just remove it entirely if the sublevel is empty. And then for iron 3 plus, it would lose from the 4s sublevel, as well as then the third one is taken from the 3d sublevel. So it would just be argon 3d5. So now we're going to talk about some exceptions to standard electron configuration, especially for transition metals. So let's look at chromium and copper. Those are probably the most commonly given exceptions. So you can see that chromium, just following normal rules, would be 4s2, 3d4. However, the actual configuration is 4s1, 3d5. So you can see that the electron from the 4s sublevel actually moves to fill the 5th empty d orbital. And then the same thing happens for copper. So instead of 4s2, 3d9, one electron from the s sublevel moves up to fill the last open position in the 3d sublevel. And this all has to do with energy and stability. So basically half-filled d sublevel, so 5 electrons, and fully filled d sublevels are more stable, and that is because, like, for example, let's look at the movement of chromium from 4s1 to the 4s2 to the 3d sublevel. So the repulsive forces keeping those electrons in that 4s sublevel require more energy than it would take to move that electron to the empty d orbital. So because it takes less energy to move it than to keep it where it is, it's more stable being moved into the empty 3d orbital. And the same thing for the copper. Why does it move from that 4s to the 3d? Because the filled sublevel, that 3d10, so if all 10 electrons are in that 3d sublevel, it's actually lower in energy than the energy required to move that electron from the 4s to the 3d. So if your resulting configuration is going to be more stable and lower in energy, an atom is going to want to do it and the electron will move. And there's also other notable exceptions to this, including heavier elements like molybdenum, silver, and gold. So lanthanides and actinides, those bottom two blocks of the periodic table. So if they are lanthanides, they have 4f sublevels being filled, and if they're actinides, the 5f sublevels being filled. F orbitals hold a maximum of 14 electrons because there are 7 orbitals. And this is their general configuration. So they fill the 6s sublevel and then the 4f, where in this n can be anywhere from 1 to 14 because there can be 14 electrons in the f sublevel. In the actinides, it's the same thing except 7s and 5f. So an important thing to note is that f orbitals are inner orbitals. So what does that mean? So when we say f orbitals are core-like, that is because they're actually in the 3D configuration of an atom, kind of buried within the d sublevels. So this can cause different chemical properties of the lanthanides that are different from other transition metals and elements that come before them. And one of these properties is called lanthanide contraction. And lanthanide contraction is when the atomic radius of an atom is smaller than expected. And remember, the atomic radius has to do with the pull of the nuclear charge on the valence electrons. Pulling them closer will result in a smaller atomic radius. Because those f orbitals are kind of buried deep within the d sublevel, when electrons are in the f sublevel, they also provide very poor shielding effect. So shielding would be if there's more sublevel, if there's more energy levels, then those electrons would block the pull from the nucleus on the outermost valence electron. But because of the position of the f sublevels, when electrons are in there, they shield very poorly. So there's actually more of a pull on the valence electrons than would be expected. And that's called lanthanide contraction, resulting in smaller atomic radii than would otherwise be predicted. So here are the electron configurations of the lanthanides. So even though the 4f sublevel would be filled for the 5d, looking at electron configuration rules, some have 5d1 electrons, so that first electron is put in the 5d sublevel rather than the 4f. And this is due to, again, energy considerations and stability factors. So looking at lanthanum here, you see 6s2, 5d1, it goes in the d sublevel, not the f. And you can see here for cerium, we have an electron that goes into the 4f1 and then the 5d1, which seems like counterintuitive, but again, this is all about energy consideration. So just know a lot of these do not follow normal electron configuration rules. So the actinide configurations are more irregular than lanthanides, if that's even possible. And that's, again, due to the very similar energies of the 5f, 6d, and 7s orbitals. Because they're so close in energy, we can have a lot of different movement of electrons in order to produce the most stable configuration. So you can see that here, for example, we have 7s2, 5f2, 6d1 for protactinium, and then uranium, 7s2, 5f3, 6d1. So we'll have 3 electrons jump into the 5f sublevel and then 1 move into the 6d. So I just wanted to make that clear again. They're so similar in energy that different configurations will occur in order to maximize stability of the atom. So again, when you're talking about electron configurations of ions, for transition metals, you're going to remove the 4s electrons before the 3d. So for main group elements, you're just going to take the electrons, if they form ions, you're just going to take them from the outermost filled sublevel, or if you're going to add electrons, you add them as if you're continuing to fill the sublevels in their electron configuration. So for example, for chloride, you would add an electron to the 3p sublevel and it would have the same noble gas, same configuration as argon, which is why it forms chloride in the first place, because then it will become like a noble gas. Calcium loses 2 of the 4s electrons to again be like argon. Aluminum will lose 3 electrons to have the same electron configuration as neon. Then the last thing I wanted to talk about was transition metals and then their relationship to color. Also, I wanted to mention zinc is technically not considered a transition element because by definition, transition elements have unfilled d sublevels, and zinc has a filled d sublevel, so it's technically not considered a transition metal, even though it's in the transition metal block of the periodic table. But anyway, so the electron configuration is inherently related to the color that the transition metals are and the color that the transition metal ions can be. There are other things that go into this as well as, like, for example, if it's transition metal salt. So whatever it's coordinated with, like for example, copper sulfate, because it's coordinated with sulfate, it's actually blue. But if copper was coordinated with chloride and copper chloride, it would be green. So its electron configuration as well as what it's coordinated with affects the color that we see. So copper normally has this 4s1 3d10 coloration, so it has a color because of the unpaired electron here in the 4s sublevel. But for example, copper plus, which loses that 4s electron, does not have a color to it because its sublevel is filled. Copper 2 plus, however, is colored because it loses an electron from the 4s sublevel and the 3d sublevel. So you can see we have unpaired electrons in this 3D sublevel. So you might glean from this that unpaired electrons have something to do with the color of the element, and that is correct. So why is this the case? Because unpaired electrons in transition metals can cause them to have a color in the presence of ligands or whatever it is that they're bound to, because transition metals are ions, cations, right? So they're going to be bound to an anion, and in that case we're calling it a ligand. And this is because whenever that ligand moves close to that transition metal cation, it can cause the d orbitals within that d sublevel to split, and then the d electrons will move in different ways across those split sublevels, which cause different emissions of light, because we know that the movement of electrons right between orbitals can cause color. And so because those d sublevels are now split, when the electrons move up to a different energy level, it's going to absorb light, right? And then it's going to affect the color that we see. So electrons are going to emit a wavelength that is complementary to the wavelength of light they absorb. Now, you might get a little confused at this because I told you that when electrons move to different energy levels, they absorb a certain amount of light and then release that same amount of energy, resulting in a specific color. So why in this case would electrons emit light that is complementary in wavelength to the light they absorb? So the fundamental difference here is that when we were talking about electron transitions, we were talking about electrons moving to a higher energy level, being unstable at that energy level, and then falling back down. In this case, we're talking about specific electrons in split d sublevels moving in order to become more stable. And so they're not moving back down. They're just moving up, and they're more stable, and they're staying there. And we're also talking about electrons that are within the same d sublevel. It's just that sublevel is now split like this. So they're slightly going to move. And when they move and absorb energy, we are going to see that, but we're going to see a complementary color to the wavelength they absorb. So for example, if you have a blue color right here, like in the 400s, so when copper sulfate, so copper is a 2+ ion, right? And when it comes in contact with sulfate, it actually absorbs light that's over here in the 600 nanometer range whenever that d sublevel gets split and an electron moves up. And so then we see the color blue. That's why copper sulfate looks blue to us. So I just wanted to make that clear. This is different than when we're talking about calculating ionization energies and energies of electron transitions, because that is when they move up and then back down. This is not the case here. This is something different. Okay, I know that was a bit confusing, but that is it for the day, and I will see you in class next week. As always, feel free to email me with any questions you have, and I will see you then, hopefully better. Bye.